Okay, seems to work. Okay, so I'm Viktor from Ericsson Software Technology, and that's a part of Ericsson. And Ericsson is making telephony equipment, mobile equipment right nowadays. In the past, it was more like other kinds of telephones. Telecom is different to IT in many ways, and I will talk about this today, how we're using Valkey in our products. Yep. So how many here are familiar with mobile networks? You use one, okay. So I suppose you know all the protocols, and so I will have a short course there, maybe, I don't know, 5 minutes. Yeah, I took an example from 4G because I don't want too much hype. It should be a little bit boring because you learn better there in that way. So to the left there we have the phones, and that's the only thing that Ericsson doesn't make anymore. They are, in terminology, they are called user equipment, because it doesn't have to be a phone, it can be a connected trash can or any other thing nowadays. Then the next one there, it's the radio access network, these antennas on the rooftops and a little bit everywhere. And there are many of those as well. And then to the right of that, there is what's called the core network. And core network consists of control plane nodes and user plane nodes. And user plane is what the data that the phones are sending and receiving to and from the internet, and including phone calls. And the control plane is like keeping track of where the phones are to make sure they're reachable when they're moving, when they get idle, when they're active. Because especially radio signaling is you want to save bandwidth on the radio. So that's in a matter of seconds, if the phone is idle for a few seconds, the radio connection is taken down. So there's a lot of signaling there. And there's a lot of negotiation about radio frequencies. I'm not going to talk about that. I've been working with this thing called MME, and all these boxes are standardized. So that's not a Ericsson product. Well, we're making this node as part of some products, but the products also include like 5G, 3G, 4G, and some of them are combining several of these roles in one product. So I'm just talking about a high level, and there are many more than these boxes. Yeah, so when in this case, this phone wants to make a phone call or send a message or something, it wants to set up a data connection to the gateway, which actually sends the data to the internet. And the gateways there in the bottom, they are part of the user plane, and that's gateways keeps the IP address of each phone, because it's not connected all the time, but from the internet perspective, from the rest of the world, it has an IP address that doesn't change, so it stays there in the gateway. So when it needs to send some data, it makes a connection to this MME, gets a message, and MME can coordinate everything, check with the subscriber database if this subscription is active, if it's and which speed it is allowed to use, and various other things, and then tells these gateways which radio masts it's supposed to connect to, and set up these things before, and then that happens all in parallel, kind of asynchronously, to make this happen as fast as possible. And same kind of similar thing when there's an incoming message from the internet to the gateway. Gateway notifies MME to set up everything, and this radio mast broadcast kind of to try to find this phone are you there? If you got no response, broadcast a little bit wider area to make it connect and set up these connections. Yeah, so and it gets more complicated. I have another picture. Here, in this case, it's a handover procedure. The phone is moving between two radio areas. And here, to make sure you don't lose any data, the gateway has to forward data to two different places at the same time to make sure that there is no glitch when you're moving on a train and streaming this conference at the same time, whatever you do. So there's a lot of coordination going on there with the high requirements on latency and all these kind of things. And it gets more complicated when you move between countries and you have roaming and whatever you can have. So there's usually like these gateways and MME is like one per country, one per state or something like that. So a few, depends on, of course depends on how many, but many more of this radio and yeah. And all of these are standardized. You can combine equipment from different vendors in the same network, and the networks are owned by these telecom operators. You probably know a few. We have one that supports Valkey is Verizon. I don't know if I should mention all of our customers and all our competitors, but let's not go into that. So anyway, this all can work together. So these are standardized. So here, the only thing that needs to be stored in the actual database is the subscriber data, and the gateways also send some information about how much data have you used to be able to keep track of charging of that. But most of this is like kind of session data. So the MME keeps track of the identity of the phone and caching, which speed is it allowed to use, and where was it seen last, which area was it, so it can be easily found. And this is all data that, in worst case, if you lose it, you can always do these procedures again and look it up in the HSS subscriber database again from scratch. You can always set up these things again. So Valkey is a good fit for this kind of data. But we don't want to lose data anyway. Let me think, was that all? Yeah, and any of these things can be interrupted by any other procedure at any time. So the phone, there is some incoming data. At the same time, the phone is moving between two places, and same time, maybe the subscription is canceled, they didn't pay, so that this HSS sends a message. So everything can happen, like everything can happen at the same time, and everything is tested, all combinations of everything. It's a lot of things that there can happen. Let me go to the next one. So this, inside one, for example, the MME, that's one that I've been working with. Björn, my colleague, has been working with the gateways, so he knows more about those. But essentially, nowadays, they are running in Kubernetes cluster. Inside our customers' own data centers, where they also run other applications. So this is just, we don't control exactly how the Kubernetes cluster is installed, but it has to be in a kind of secure. I don't think any operator can run it in like Amazon or cloud or anything like that, like public cloud. It has to be like, so, I mean, maybe theoretically, but no, it's not, in practice, it's not how it's done. So these phone operators are big companies with their own data centers. So, yeah. So any network traffic, whether it's from the radio antennas or from gateway or from anything else, it comes in through a network. We have, in this case, we have a content-aware load balancer that it can match on the packets of the data which phone it is about, which user equipment is about. So it can forward this one always to the same application instance, it's a container with a process running the same application. But so the benefit of this is that we can store some data inside this application instance for this user, and so it's there each time. And with this, that makes us, we don't even have to ask the Valkey cluster about this data. Not always, we can even have it cached there. And there's no risk that anyone else can write to this data. It can affect this user. Because if I go back, I want to go back again to this one. If there's anything happening, so if the subscription is changed, for example, then the subscription will notify the MME. They all notify each other. The information is pushed forward to the network. So there's no risk that, I mean, we don't have to look it up again in the database. So when it's changed, this application instance will get notified. Yeah, so I want to go now inside this. Okay, we're using Valkey cluster. We have a Valkey operator there, which is, well, we are not using we are using some fork of an old one that was open source. We would like to have a better one. So we're looking forward to you guys provide a good one that would be official Valkey operator. We have a lot of metrics as well. We have this Redis exporter, which is, they write now on their webpage that is a Valkey exporter, which also supports Redis, basically. Yeah?
Sorry for interrupting. Can you give us some information? What is the Valkey operator?
Okay, it's a Kubernetes operator that does kind of, if one of these nodes crashes, it starts up a new one, a new container, and can set it into the cluster, configure it, and also scaling, add more nodes, remove nodes depending on what we tell it. I mean, so it's a kind of controlling, yeah. I don't know what to call it. I think it's called control plane of Valkey in other setups. It's a Kubernetes operator. It's usually used for, we have operator for our application instances too, but yeah. Björn, you want to fill in something what the operator is doing that I didn't mention?
Yeah, I can comment on the operator. We have operator for MySQL, Postgres, MongoDB. Basically, operator in Kubernetes world, you looking to replace human work. Basically, whatever human will do with databases on a day one, day two operation, which is mean setup, configuration, failover, mechanism. It's all kind of built in automatically in operator logic. So operator can manipulate cluster nodes or database instances, basically automatically without human interference. Basically to replace human in how you manage databases.
So another example is rolling upgrade of the whole system. So we upgraded application instances where we update cluster instances too, and make sure that we don't have a downtime. And we also have very, very fancy requirements. So even if we upgrade the Valkey cluster and some other microservice, the upgrade fails for some reason, then we want to roll back the whole rolling upgrade of everything. We want to be able to downgrade again. So there are, and all these things are tested in, like everything has to be like, even if it's not supposed to be able to happen, it still has to be, yeah, it still has to work if it happens. I hope that's at least an overview. Now I'm going to the application process, and in this picture I have workers, and it can be any kind of code, but a code running for a single phone at a time, we can say. And this particular software I've been working with, we are using Erlang, which is a language where we have lightweight processes. But it's kind of similar in Go, where you have these Go routines, or in other languages you can have asynchronous way of programming. So you can have multiple work going on in parallel for different users. And we have a client, a cluster client that's depending which system we have the ones, the gateways are written in C. They are using high-redis, basically high-redis cluster. We're using the asynchronous API, so we don't use any blocking. We just massively pipeline all the commands to the nodes, and the reply is matched to so sent back to the right worker. And so there's no connection pooling. I guess it's similar to Glide from what I've heard about it. And we have also some overload protection. If there are too many commands sent, for example, we don't want to have more than, say, 10 or 20 commands in the pipeline. Then when we queue them up in the client, and whenever a reply returns, then we can send the next command to the pipeline. And then when the queue inside the client is full as well, then we start dropping. We just immediately return too busy back to the worker. So there's just protection against that. So worst case, we just don't serve data, but we don't get stuck. And lots of metrics and alarms to be able to send this information back to other systems like Prometheus to watch over this. So we can do things like scaling according to this. Of course, when you have this set up, we cannot use blocking commands. That would block the connection. We had a connection pool before, but with the connection pool, you check out the connection, do a synchronous command, get back again. They had to use something like 64 connections to get the same performance, but it's just better to do it like that, single connection. It doesn't get faster if you have more connections between the same two nodes. Valkey still has to handle all the commands, so just less overhead, fewer connections. Go to the next one. So we have inside the application process, we also have some in-process cache that I talked about before. That's since we know that all the traffic for the same user is going to end up in the same application process every time, we can store things even faster than Valkey. We store it inside the process in a cache, or call it a software transactional memory, which is basically a thread-safe hash table inside the process itself. So it's faster than communicating to Valkey over the network. So I had some animation there. So first thing, when we have something to do, we can load the session data for this user into the worker. Usually it's there, so we wouldn't have to go to Valkey for that. Do some work, talk to blah blah different entities, and then when it's done, we save it both back to this one, to the cache, and to Valkey. So with the setup, we have almost only writes. The load we have to Valkey is just as long as nothing happens. Like we use reads when there is when we have a failure, worker failure. We need to start a new one, and it doesn't have anything cached. And when we scale, when we scale, a user ends up at a new instance where it doesn't have everything cached. It reads from Valkey. So Valkey is essentially a cache, and it's essentially a backup, while many other systems use it as a cache. Yep. Next one. Oops. What happened to this slide? It's empty. Okay, doesn't matter.
Sorry, I had a question.
Yeah.
How many objects? How big is like for one subscriber the amount of data that you store in Valkey?
The amount of data for one subscriber? I don't know.
Is it 2K or something? I don't know. It's
just roughly, yeah. Just an idea.
You would know as much as I do about that.
it depends. It's different. The different boxes have MME, SGV, PGV, although they have different kind of data as well. So, and it's all use Valkey.
But it's essentially the user identity. They have a global unique temporary identifier, and they have some. Yeah, I mean it's not a lot. It's the metadata about what frequencies they're allowed to use, where it is, which region
From 2 to 10K maybe. Or
Yeah, it's not more than a few K. Yeah. So it's stored usually in hash set and yeah, and sets and various things.
So Victor,
Yeah.
question here.
Yes.
One of the first slide you mentioned you can't lose data. If I remember correctly, right?
We can do.
You cannot lose data.
We
right?
cannot. We don't want to lose data.
Right, exactly. How do you do that in this setup specifically with Valkey?
So I mean, worst case, if we lose data, if we lose Valkey, we can always go back to the subscriber database. That one cannot use Valkey. That one has to use a proper database, like with real guarantees, and the ones that handling subscriber information. But if I go back to, let's say, this one, if a Valkey node is down, the client can queue up, and even in this one, we can let's say here the write to Valkey fails, we can queue up these writes inside the application. So after a failover, after a few seconds, we can store it. So we have some extra safety for that to make sure we don't lose writes. But worst case, we can lose writes. You know, it's Valkey. So yeah.
Got it. So you go to the database, the worst case.
Yeah, but then the phone will kind of have a glitch of some milliseconds more. Yeah, there will be some more signaling in the network. Yeah.
Thanks.
But it's not. I mean, it's not something you will notice probably anyway. So. Thanks. Anyway, for this slide, I have some notes there that you don't see. But many times, oh, do I have? Okay, I have. They're coming. So we have 6 nines. It's our target of reliability uptime, which is I think higher than many IT solutions, and it's at least 5 nines in practice. Often 6 nines. That's the aim. And I always mention that we plan for the impossible, have all kinds of testing, that even things that are not supposed to be able to happen, that if they happen anyway, that we handle them as good as we can. Overload protection. I already mentioned that we can drop writes to Valkey. We can also drop packets, network packets. If we're reaching something like 90% CPU, we start dropping packets just to be able to handle the load we have, so we don't get stuck. And all these nodes in the network, they will resend data after some time. So hopefully that will still work, but with some delay. That's how it's all designed. That's all standardized in a way. Yeah, fault tolerance and minimize damages if anything happens. So for example, I already mentioned if Valkey is down, we can still serve data. We can still find most of the data in the cache, and it doesn't affect anything. And yeah, we collect a lot of alarms and events. That's important for operators to be able to observe everything. And yeah, that's all I have. And that's our logo, and that's my email address. Do we have more questions? Yeah?
Sorry, yes. So if I understand it correctly, you are building a piece of software for the MME that you're selling to the operators, right? Is that Valkey is part of that? Is that right?
Yeah, MME is part of the software that we're selling to the customers. Yeah.
Yeah, got it. Okay.
And Valkey is included. Yeah. So it's Valkey is not something internal. It's just microservices as part of the software.
Thanks.
That means we can control all the clients that connect to it. So we have full control of. We don't have some clients that misbehave that we don't know about or something like that.
Okay. Thanks.
Yeah.
Thanks.
Is not needed. So in your slide, I saw that your application instance has connection only to the single Valkey instance, right? Correct? It's somewhere in the beginning, right? So
I have this one. It has
no, the previous one. I think it's yep. a bit forward, a bit forward. Yeah, here, right? So you have application. So each application instance, right, is only connected to the single
Oh, no, it's connected to all.
to the mesh, right?
To the mesh.
Correct. And how do you? And basically, you don't care about the data consistency, right? Too much, because in worst case, if you don't find a subscriber on a local your MSS, so you could always connect to the MSS and check that what kind of data, right?
Yeah, but I mean, the Valkey cluster is consistent hashing. We always know on which node each key is stored.
Okay, I see.
So it's not
So because the question is how we replicate, right? So you only replicate, not all of them replicate in one from each other, right? Correct? So only,
Valkey cluster is sharded. So if
Okay.
it's each shard is like horizontal scaling, and the replicas are providing high availability for those.
okay, so basically for all your application instances, it could connect to any machine, right, in your Valkey cluster, and it gets all the data needed, right? So it's shared between all the obviously between.
I
all
think each of the application instances has to connect to all of the primary Valkey cluster nodes,
Okay.
because it's not designed in this way that only some cluster slots go to the same application instance. It's no, so they have one connection, like this picture. They have one connection to each Valkey node, because.
So basically, application mostly it's responsible for the data consistency, right?
But we use these tags, the curly braces in the keys, so to make sure that all of the data for one user is stored in the same Valkey node.
Okay, I see.
Yeah, that's
Thanks.
something you can design your keys in the way that to make sure they belong on the same node. Yeah. Okay, thank you.